All right. Happy Tuesday. There we go. I hit the record button. So I got this message from a guy in the University of Amsterdam. He said, "Hey, take a look at this cool thing I do. I noticed you teach Python." I was like, a weird message, but sure. Like, he's not selling it. It's just an open source thing he built here. So you can visualize all sorts of everything in Python. All of the data structures we've been talking about, he has visualizations for using this really cool tool. So you can see what's being stored where in memory, sort of a visualization of it, which is really cool. So showing how copies work here. We'll get into what's being stored in memory when I have a list of things here. Right, here's my range, here's my tuple, here's the set, here's the dictionary with keys and values, here's a class, attributes and values. Seems really cool. And then, oh hey, I make A and B point to the same, B equal A, now they point to the same thing. Right, and you can see that visually here, rather than just me telling you, hey, they have the same memory address. Right, and he's got all sorts of other fun ones in here. What was the other cool one here? Mutable types, custom copies. You can see your call stack. The data model. So here's a binary conversion bit here. So he's showing you how you're converting to binary. Oh, look, I can div mod. Apparently that's a built-in divide modulus here function. Didn't actually know that. So it gives you back the quotient and the remainder. So you don't have to do two division step and modulus step. You just get it both back at once here. And it's showing you, hey, let's build out this. So that's kind of fun. Powers, so running in the debugger. We're about to do circular doubly linked lists. We just haven't got there yet here, and we'll show you, hey, what points to what. So usually I draw this out by hand, and it'd be really cool to just click a button and have it show here. I thought that was really cool. I didn't install it yet because I wanted to like actually Google the guy real quick, make sure he does work there. Um, and then I would go install it. So maybe for next week I'll have this ready to go, and you'll just take my word for it with my pretty pictures. But we'll get there where we can see all these sorts of things here. We'll get to binary trees. You can see trees. So really cool to visualize it, kind of get a better picture of what's happening here. And the guys I just wrote this open source project because he teaches it, and it helps him teach it. He's like, it might help you too. So this is why I really like the software industry, because people just do stuff and they're like, this is cool, you should use it. Some stuff gets licensed and there's money for a lot of things here, of course, but um, everything is running on open source projects essentially because people are like, this would be nice to have. I'll write it and then I'll share it here, and that's super cool. Our cybersecurity friends don't like that because then we're dependent on essentially one random person somewhere, who knows where they are, maintaining a project, and we get vulnerabilities and things by not paying enough attention to those sorts of downstream things. So is Notepad++ malware? Let's see, I just read about this one. Yep. Um, so yeah, this was just recently here. Um, Infrastructure level compromise. So they're compromising Notepad++ through all of its dependencies and other things here, getting since June 2025. Likely the Chinese state-sponsored hacking group here had targeted Notepad++ to add malware to it here. So anyone using it was inadvertently getting malware here. And this was a relatively widely used tool. Still pretty popular. It's been fixed now. I mean, fixed. It. So yeah, it's no other clients hosted on this. Yeah, shared hosting server in question was compromised. Why do I have to scroll right and left on this? Come on, you know that's bad form here. Um, yeah, rotate it, check the logs, update your WordPress site. Oh my goodness, WordPress sites, they always get hit here. Change your credentials. Yeah, do bad. Check all that stuff here. Yeah, download the new version. So those sorts of dependencies are rough here. Like Notepad++ doesn't charge for their tool, right? A free tool, and people use it because it's good. Does a bunch of cool stuff here. Um, so like, I don't know. Don't think too hard about it, maybe. But it is a risk here. Doing security assessments on that sort of stuff is rough because you saw we installed one package and it installs all these other packages, right? Just to get matplotlib. Like, oh, now I also need all of these ones here. And do I know anything about those ones? I don't actually. So that being said, though, libraries are cool. We like them. People write cool stuff here. Um, and bad guys make it so we can't have nice things. Tends to be how that all worked out here. Did I ever tell you the story about Facebook when they first created it here? Um, there was no intention or thought ever put in any security tools at Facebook when they created it because your real name was associated with your profile. Who would do bad things with their real name? Again, we just sort of trust people will do good things, and then they're like, "Oh, look at all the cool things I can do now, and I can be a fake person and be a predator." Like, oh, maybe that's a bad assumption. So those sorts of planning to make sure that software can't be used in bad ways is very difficult here. When you get more into software engineering and all sorts of fun things, we call them abuse cases. So we talk about use cases. Hey, my software should do this. Right? I have a use case. I want to go in and do this fun thing. And you think about abuse cases, you're like, oh, software can do this. How can I take advantage of that? How can I do a bad thing with this cool feature? And then we figure out how we make it so you can't do those bad things, that sort of stuff. So just really interesting here, a little depressing, but that's okay. So we play our PyCharm here. We are in this week 6, 5, because I started at 0. Everyone starts counting at 0, right? Week 5. Okay, week 5. We start a new project here. So linked lists is going to be completely different from anything we've done so far. And the reason why it's completely different is it stores things completely differently in memory. So let me pull up a new project here. Goodness. And they're going to be really fast at some things and really slow at other things. Just like our regular array-based lists, we're really fast at some things and really slow at other things, right? Removing from the beginning of a array-based list here means everything has to shift. That's really slow when I've got 10,000 things, 100,000 things, a million things in a list here, right? We don't want to be doing these slow things here. So we'll take a look at a different data structure that can be faster at some things here. 5 linked lists. Make my welcome script. Don't I want? Yeah, project. Okay, virtual environment. Good. Copies off of that one. Coffee. That's so sad. I didn't bring my thermos in to refill at the gas station because I was running behind. Um, the guy was really. He sees me like every week now. He's like, "Oh, you didn't bring your big mug?" He's nice. He only charges me like one refill to fill the whole thing. Like it takes a pot. You can charge me like 2 or 3 or 4 refills, whatever you want. He's like, "Oh no, it's fine." Probably because the coffee's old at that point. Like they make the coffee in the morning, and now I'm drinking their leftovers. So, all right. I'm not too particular, but McDonald's coffee has been really bad lately. I think the one by my house is just, I won't actually finish it. It's that bad, which is surprising because I eat everything. Anyway, so a linked list here. So the idea with a linked list is that each piece of information in your list knows about the next piece of information. So I can't get at any of them. They're not a contiguous block of memory. I don't need to know where they all are. I just need to know where the first one is, and the first one will tell me where the second one is. The second one will tell me where the third one is. The third one will tell me where the fourth one is. So you imagine it's sort of like if you walked in the door in the classroom here and I gave the first person who came in a piece of paper. I'm like, okay, I know who the first person is. And then the first person writes down the second person's name. And then you give them a piece of paper, and the second person writes down the third person's name, and the third person writes down the fourth person's name. So I could go to the first person and say, who's next? And go to the next person and say, who's next? So you don't all have to be in a line as long as you know who comes after you. You don't have to show up in a big block here. You can be wherever you want in any of your seats here, and I'll just call on you in order. All right, you came first. Who is next? All right, who is next? All right, who is next? And go around and around and around. So that way, when we are storing a bunch of values in memory, I don't need to ask my operating system for a giant chunk of memory that's contiguous. I don't need to say, hey, give me room for 10,000 things here. And by the way, it has to be one big chunk of memory. It can be anywhere. Yeah. So all I need to do is allocate memory as I'm adding things, and I'll just add them in. So what we do, we build these things called nodes here. And this is actually a part of our linked list class. So our linked list class has an inner class for node here. And then what node has is it has the data and it has its next. And I'm going to assume you don't have anything after you until I know otherwise. Right? That's all it is here. So, and then we'll have self.data is the data, and self.next is the next. So this private inner class here, no one else needs to know about nodes here. Like it's just an implementation detail. So when we're talking about working with linked lists abstractly, no one ever touches a node. they just work with my linked list and they know, okay, I can get this item, I can get this item, I can get this item, the things we can do with a linked list. So things we can do with a linked list are all the things we can do with lists, right? So we'll have our init here. So we have self dot, we need the front node here. So this will be private. No one needs to know how I'm tracking it here, but my front here is going to be a none until I know otherwise. And then I'll have a number of items is 0, right? And then you can, let's do append. So you can add to a list, right? Um, so that would be just the item here. And actually, let's make this easier here. So let's do add to front. We'll call this add to front. So we'll add a new front item here. This will be a little bit faster for us. And we'll get to some of those other options when we get there here. And then we can remove the front thing, remove front. So eventually we'll return something here. I'm just going to put none for now. We'll come back here. Do remove front. Did I do it wrong? Oh, this one here, add to front. We'll just return for now. To do, I think pass is I should just call it pass instead. Let's say pass. There we go. That's more Python idiomatic. All right, so you can add to the front, you can remove from the front, and then we can like peek at the front, essentially. So, like peek here, or we'll just call it front maybe. And so it doesn't remove anything, it's just going to show you what's at the front. So this will act similar to a stack at this point now, right? If the only thing you can ever do is put them on top in the front here and take them from the front, we're now a stack, right? But that's okay. So we'll get there. So to add something to the front here, right? If my front is none, I have a new front, right? If I do have something in the front, that will now become the next thing. So it'll be the new front's next here. So what I can do is I can say, I want a new node. So self.front then will equal self.node given the item. And the next thing for that one is the current front. Right? Whether or not that's none or not here doesn't matter. It now knows you come next, and it might be nothing, it might be something here. So we can imagine, let me do some drawing here because that's always fun. So usually we do nodes with these little rectangles. I don't know why here. When we have our data on this side here, so maybe like the number 2, and then this will be the next. So this is the item or the data, and this is the next here. I really should bring in my drawing tablet. That'd be a lot easier. So if you have nothing here, you usually put a slash in for none. Otherwise, you'll say, hey, the next thing is this thing over here. Right? It will point to the next node here. Right? Okay, maybe I have another node over here. So now I have maybe a 7, and this one is next is none. Right? So if I add in a 7, its next is none. If I add in a 2, its next will now be the 7 node here. So I can get things out. I can remove things from the front here. So that adds to the front, and then I take my self.number of items plus 1. Right? To remove the front thing, I need to give you that piece of information here. So I'm going to have the item is my, I guess we should check first. So if self.front, or if not, maybe self.front. So if it's none, it's false. If it's anything other than none, it's true. So if it's none, then this will be true. I can raise a value error or something here, empty or invalid, whatever error. It doesn't matter too much here. If it's not empty here at this point here, or we can even add in, I guess we could add in a helper here, define is empty, return self.front is none. So if we're none, oh, we can just return self.front, right? No, equals none. Oh, is none. That's right. Not equals, is none. It doesn't like the double equals there. Sorry. So if front is none, we're empty. We could do that too then, right? So if is empty, self.is is empty. That's probably a little bit nicer here. Okay. Other than that, I can give you back that item. So the item then will equal the self.front dot item, and then I need to move front. So if I'm going to remove this value here, I'm going to store that value here. So now I have the 2, and now my front just goes to this front's next. So now it moves to here, this node. If it's none, it's none. If there's a node there, there's a node there, right? The code should still handle this. So now my self.front equals self. Now this is where it starts to get crazy here. That we'll say front.next. So self front is the front's next. So we're following that pointer here of where is the next thing, okay? And then the front itself or we just return item. So we can do the exact same thing for this one here. Give you the front thing. We just don't move front. I guess we just return this self.item. And then maybe we have a length as well. We can define length, return self.number of items. Oh, we should probably reduce that, right? When we remove something, self.number of items, -1. Okay, we've taken something out here. So now I can use my linked list here, uses the node. What is it not like? Oh, it doesn't like next. That's fine. So I can make this is essentially my stack here. Stack equals a linked list. And then for number in range, let's go up to 10, make my stack dot add to front here, the number. And then while my stack dot is empty, not is empty, we'll print the stack dot remove front. We should work exactly like our stack. Oh, I hit the debug button here. So, stop. Let's run. Oh, node has no. Oh, node doesn't have item. It has data, doesn't it? Yep, it's data, not item. Node dot data. Should just call it the data. We should call it item. I like item. Node dot item. I should have just replaced that. Okay, that's fine. Item. I think we're good then. Item. Let's try that. Hey, right, and we get stack behavior. So now what's cool about this is there is no array list behind the scenes. There's no list behind the scenes. No matter how many things I add to front, it will always be a constant time operation. Not even just on average, but always. Right? There's no doubling that we have to amortize over and say, sometimes it's slow, but on average it's still fast. It is always fast. So the guarantee for this one, right, is O of 1 always. So best case, worst case, average case. And mostly we care about average. Sometimes worst case is important. No one ever cares about best case because that's never going to happen, right? It only happens once. So average and worst are the important ones here. So our worst case is still O of 1, no matter what here. So this is ridiculously fast, which is really cool. Now, the downside of this is we've traded off a little bit of memory usage because every piece of information I'm storing is also now a node. So I'm storing essentially 2 things for every 1 thing. But if you think about our array-based lists, we still had to double our size. So I had half of my array was empty. Eventually it was less than half, and then I got down to full, and then I had to double again. But we were still trading off space. So at some point with our array-based lists, our space complexity was still doubled here based on n here. So even if we're doubled based on n, we're not really any worse off than we were with the array lists. So we were using a little bit of extra memory here, but this is super fast. Now removing from the front here. Now, when we used our circular queues, we were able to make this really fast, right? And removing from the front. The stacks were always fast because it just took from the end, added to the end. With a queue, this was a little bit slower. And removing from the front of a list here was very slow because it always had to shift those end things over. So with this one here, again, we are always O of 1 here, no matter what here. Front is always O of 1. This one was never slow here, so that was okay. Is empty and length, those are always fast too because we just track those variables here. So this behaves very quickly as a stack here, right? So maybe we'll call this our linked list stack, actually. We'll call a linked list stack. Okay. Now to make a linked list queue, I need to be able to add to the front, I need to be able to add to the end. This gets a little bit harder here, but what we can do is we can just track where the front is and where the end is. We already know where the front is, so now let's just know where the end is. So the problem with making it a queue is to add to the end, you have to go find where the end is. So I'd have to say, hey, front, what's next? 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 And that would be a slow operation. The book will go through and write that version, and they'll be like, hey, look, this is slow. Can we just assume or acknowledge that, yes, that would be slow, and then write the better version? Okay, all right. It's a fun thought exercise. We'll make it faster here. So let's do a linked list queue here. Linked list queue. Now we'll have a self.back. So if I know where the back node is, I can always add to the back really quickly here. So we'll have no longer add to front. We'll call this one append. right? Or do you want to call it add to back, or you want to call it NQ? We can call it NQ, right? We could, so we could be a deck at that point with an add to front and then add to back, right? Um, yeah, sure. We'll leave it add to front, I guess. Add to front, and then we'll add an add to back. So define add to back makes the item. Now, when we're adding to the front here, if my back is none because I'm empty, my back now is also the front. If I already have a front, the back doesn't change. So there's one extra special case I have to worry about now, is if my self.back is none. Then my self.back equals the self.front, right? Because now the front and back are the same node. I only have one thing. So I can either add in front of it or I can add behind it, right? But it's the same node here. So there's a little bit of extra special handling we have to track for the back here when we add to the front. Now adding to the back, right? We could, if we're empty here, then front and back are the same. So what we can do, we can sort of cheat here. We can say, hey, if self dot front is none, or if self dot is empty, I guess, right? Self dot is empty. We'll just, oh goodness gracious, we'll just call self dot add to front, given the item, because this one already handles the front and back bit here. And then if we're not empty here, otherwise, I'm just going to add it to the back. If I'm not empty, I must have a back node. So now what I can do is I can make a new back node. So my self.back dot next is going to equal a new node of so self.node given the item, and then the next is none, right? Because it will be the last thing, so it doesn't have a next. So I don't even need to give it anything here. Its next is none. So say the current back, you now have a new thing, right? So if we add to the back, we'll say, hey, 7 over here, you now have a new thing at the end here. Now you have an 11. Its next is none here. And then you're no longer none here. You point to the next thing, and then self.back is over here, right? So we have the front, and we have the back. Ah, that's a really long F there. Front. There we go. Front and back. Right? So we can handle that pretty nicely here. Now, all we need to do is change where back is. So then self.back then will equal self.back.next, right? Add something to the current backs next, and then next is now, or it's back now, it becomes that one. So we've added it in. So we've added the back, added to the front. We just had to add our special handling here. Front and backs are good here. Removing from the front. Now, this one we have to be careful with because if we are empty now, self.back needs to change as well. Because self.front was just moving to the next. It could be a none. So if it becomes none, then back also needs to become none, right? To make sure that all of our logic is going to work well. So we can say, hey, if self.front is none, then self.back is none. Right? If we become empty, make sure that back is also empty now. Right? So our special handling here. Front works the same way here, but now we can have a remove back. Define remove back. Okay, so this will have to do the exact same thing here. But now this one gets to be trickier because if I want to remove the last thing here, where does back go? Back needs to go up, go back one, but I don't know how to get there from the back. And my back node doesn't know what comes before it. It only knows what comes after it because these have single links. These are called singly linked lists. Just a link going to the next one and the next one and the next one. So the only way to reset back now is to go to the front and go to the end. So that's not good because we don't want that. That's going to be really slow here. So what we're going to introduce now is a second link. Will be a doubly linked list. So not only will nodes know what come after, but nodes can know what come before it because I want this to be fast. So I'm going to track what comes before you. So you'll be linked forwards and backwards. Right? So you'll know what comes before you, what comes after you. So to do that now, I have to go to my node, and we have to add in a self.previous. Is the previous. So we can default that to none here. Previous is none. If you don't tell me here. So when I make a front node here, its previous is none. There's nothing that comes before the front. Easy enough here. When I add to the back now, the thing that is previous is the current back node. So it doesn't have a next, so we can say next equals none here, but previous then will equal self.back. the current back. Now, you don't need to name them here. It just, as we're dealing with fronts and backs and next and previously, I get confused really easily. So I like using the named parameters. That's just me. I'm a little extra here. And I think that makes it a little easier to read here rather than having to remember this one is next and this one is previous is all. Okay. So we set that one. That one's good here. So removing from the front, we go remove that item here. But now the current front here, after we've moved, is not going to have a previous. So we need to break that previous link. So now we can say self.front.previous, front.previous is none. Right? We've removed the front thing here. You don't have one anymore. Right? So you're now the new front. Nothing comes before you. Okay. So let's see if that keeps all of our links here. I think that should be good with our links, right? So we're adding in, doesn't have a previous, so that's none. Okay, just has a next. Back is the front, add to the back here. We're setting you come before the back. That should be good. Doesn't have a next here. Removing the front, we break the previous link. That should be good. So we're moving from the back then. So we have our item. Then is going to be, we should check if we're empty first, I guess, right? If it is empty. Now I have the same code a couple times here, and I feel bad about it, right? So if you have the same code twice, you should feel bad about yourself. So let's change it. It's only going to save me one line of code, but that's okay. So I'm going to go to refactor, I'm going to extract method here. We'll call this check empty. And we'll make this a helper function here, check empty, because no one else needs to do it here. And it says, hey, I found another place. Do you want to replace that one too? Yeah, we'll do the same thing. So we'll check if we're empty first. Because if we're empty, we should raise that exception. This just makes my code a little bit cleaner looking, I think, here. So to remove the back, if we're not empty, then my item will be self.back.item, right? And now I need to move the back to that last previous. So self.back can become self.back's previous. Then my current back, the new back, should not have a next. Right? It should have been linked to that one, right? Its next should have been the old back. That one needs to go away. So then self.back.next now will equal the none. Okay. And then if we're down to just one item here, that should be okay, right? Because we're just the front at this point here. That one should be okay, right? We're just changing back here. If we have no items left, though, we're going to have a problem. So if self.back, I guess before we even check this, right? If self.back becomes none here, so if self.back is none, then self.front is none, right? If it's not, then I can set its next to none, because if it is none, there's nothing to set here. It's just going to stop. So we should probably check that on our front here. So we remove the front. Yeah, we got to check that if it's not none here. Else, so if it's none, nothing. Otherwise, we can set a previous here, and then our number of items goes down by one. That one's good. Should include that one here, and then we can return the item. Actually, we should put that in the same spot, right? So we're matching. Move it down one. All right. So that matches. Looks the same as that one, I think. Right, and then we have a back as well. Right, so you can get the back item. Check for empty and return the back.item. So it should work now as a queue, right? We should be able to add to the front, or as a deck now, right? I guess this was our deck. And we went right to, does it not have the extra UE? Did you ever wonder here, which is the silent letter in Q? Is it the silent E, the silent UE, the silent UE? Do we have 4 silent letters in the word Q? All right, anyway, sorry. So let's give it a try. See if that one works for us here. So our stack was fine here. Let me just comment that out, I guess. We'll leave that commented, and we'll try our deck. Oh, I didn't add the number right when I added to add to back. Oh my goodness, I can't even find it. Add to back, remove front, Add to back, thank you. Self dot number of items, +1. Not equals +1. All right. So let's try it here. So we'll say for number in range, let's go 5. Let's take we got to make our deck here, right? Deck DQ equals a linked list deck. And then our deck, you want to add to back maybe the first bunch of numbers here. And then maybe if we go for number in range, let's go from 5 to 10. Let's take our deck and we'll add to front here the number. So we should get 5, 6, 7, 8, 9, 1, 2, 0, 1, 2, 3, 4. Right? If we added these to the front, added those to the back here. And then let's remove them. Should we go backwards and see? I don't know. So while my deck is empty, not as empty, I always forget that. We'll print the deck dot remove from the back. See how that works? Uh-oh. You only got 4, 5, 3, 2, 1, 0. Something didn't quite work here on our add to front. I think here. We can try it and see. So let's put it in debug mode and see what we have here. So we have our deck here, right? It's got a node, right? That's the node class itself, but these front and backs here. This is what we really care about. Its front is the 0 and its back is the 4. So far, looks like we're tracking those okay, right? So now we add to front, let's step in here. So we're saying, okay, front becomes a new node. Self.back is not none here. So we should have just set front, right? So front should be the 5. Good so far. Its next is the 0. Good so far. Right, add to front, step in, change the front here. Front is now the 6. Okay, that looks good so far. So I think that's working okay. So maybe it's the removing then. Remove from the back. Let's see what happens here. So we checked it for empty. We got the back. Back becomes the previous here. So my back was the 3. Right, its previous now should be the 2. Looking good so far. Self-dot number of items goes down by 1. Do we set that? Back's next is none. That should be fine. Right, and then we'll step in again. Oops, that was empty. Here, remove back. 3, setting that one here, move, step in. Now this one's going to be the 2. Right, items 2, good so far. Step in, items the 1, good so far. Step in, items the 0. Okay, good so far. So did back get set properly here? No, back got set to none. Back's previous. Why do we not have a previous of that one there? We called add to front. Did add to front not set the previous rate? Let's see. So we're adding to front here. It shouldn't have a previous. Nothing came before it here. Just the next. Oh, so what we forgot to do here is now we're going to do, so we said, okay, let's add something to the front. So this was node 2 here, right? It does not have a previous here. It's the current front. We said, let's add something new. So we added a 5 here. So we made a new node here. We called it 5. And we said, its next is this one here. And then we said, oh, by the way, this is now the front. What we forgot is the previous now. So now we have to go in, we have to say, okay, now the self dot, this is, again, a little nuts here, that's okay. So this is the front's next previous is the self dot front, right? The thing that comes after me, the thing that comes before you is me, because that's the only way I can get to the next thing is by going from the front to the next thing. To tell it its previous thing is me. So the way that we walk these chains here, it's a little bit weird. So the front's next node's previous node, right? It gets a little weird with these circular links as we're walking through them here, but that's the only way I can reference it, right? Because it doesn't exist yet. So I can't say, hey, current front, you now have a new previous because I don't have a node yet, right? I've set for, I guess I could call it a new node if we wanted, but that might be a little easier. So we'll save these two for a second here, and we'll say, let's do this a little different here. So we'll have a new front then equals a self.node of the item self.front. And then the self.front dot previous is the new node, new front, and then self dot front equals the new front. Is this better than this here? Is that a little more clear what we're doing? I think that might be a little cleaner here, right? And hey, we get paid by line of code, right? So why not write 3 lines of code versus 2? Or Elon Musk came out and is like, all the engineers must have 10,000 lines of code a month. We're like, that's not how it works, buddy. Tell me you don't know how to code without telling me you don't know how to code. No? Okay, never mind. Sorry. Um, I have issues with that guy. But that's okay. Is this one a little better? Does the same thing here, right? So same as below. Below, but easier on the eyes. Okay, I'm making a new front, setting its next, telling the current front it now has something that comes before it, and then changing front here. Right? That's probably a little nicer than the front's next, previous is next is. That just gets a little ugly here, right? Okay, so now we have our queue. Let's see if it runs now. Oh no. Front's previous equals new front. Oh, we broke it. None type. Oh goodness, we forgot to see if it's none. Right? If it's not none, right? Because if it was none, it can't set anything here. So if self.front is none, is not none, then I can go set these things here, right? Otherwise, I didn't have one here, okay? Probably I could do the same if my back is none, right? No, this is if it's not none, so it'll be the opposite here. Okay, should be okay. So we're just adding a little sanity check here. When we had nothing, I couldn't go set the nothings previous. It just didn't exist. So I only have a front with nothing before it. Let's try that. Well, now we got nothing out. Is that an improvement? I don't think that's an improvement. All right, what did we break here? Let's see. Run the debug. All right, we've got our 5 items in the deck here. Let's go add to the front. New front. Have a new node. Self.front is not none. Self.back. Oh, wait, why did it skip over that? It's not none. It shouldn't have been none. Self.front. It was none. How is it still none? Oh, this line. Sorry. I should have just kept this. I guess this would error too here. So we always have to set front to the new front here. We're only setting the fronts, old fronts previous if we had an old front here. Let's try that. Hey, all right, now we get our numbers out. So we get 43210, which we added to the back here. So we added a 0 to the back, 1 to the back, 2 to the back, 3 to the back, 4 to the back. So 4 should have been the last number that was added, right? And then we added numbers to the front, 5, 6, 7, 8, 9. So we pulled them off from the back. Right? It was the last thing added to the back was the 4, the 3, and the last thing added to the front was the 9. So I think we got it in the right order here. Does that match what you're expecting? Okay. I'll take my word on it. So let's see if we can remove from the front. Let's try it the front order here. Now we get 987654 or 98675, 0, 1, 2, 3, 4. So I think that's working okay here. Right? The only thing we might want to check here is removing a couple from the front, a couple from the back here, making sure that those we can do them kind of interchangeably here. So maybe we'll just print back.remove front and then print deck.remove back here. And then while my deck.is not, deck.is empty, print deck.remove from the back. So just try one here, make sure it doesn't break. Yep. We get the front thing, we get the back thing, and we just keep on taking off the back. I think it's going good so far. So we have now our doubly linked list. Now, the problem with this one here, let's talk about how fast it is here, right? So it should always be constant, right? So this O of 1, right, when we add to the back, because we know where the back is, I don't have to say, where's the next thing, where's the next thing, where's the next thing. We never did the slow one, right? We went right to the fast one here. Removing from the front, removing from the back should always be the same O of 1. right? We never have to go find any of these items here. Nothing ever has to shift, right? So if I take something out, I don't have to move what was 1 to 2, what was 2 to 3, right? Anything like that. Nothing has to shift here. All right, so now we've got the linked list deck here. Now, the next thing we can do to clean this up here is we can make this a circular doubly linked list. And that's going to make our code a whole lot cleaner, because what we're going to have is what we'll call a dummy node that is always there, so we never have nones. See, all this none handling is really ugly, right? Setting, checking if it's none, seeing if it's none, dealing with nones. We have a bunch of extra handling in here, right? And as you can see, that was error prone, right? We definitely ran into issues. I did that totally on purpose to show you this is error prone when you have to deal with nones here. So what we can do instead is we can make this a circular doubly linked list here. We'll call this a circular doubly circular. There you go, not two R's. And we'll just leave it as a doubly linked list. So we'll add in some other features here. And we'll look at, so the circular version is the best one here. So now our node is still doubly linked, but no longer do we have a front and back here. We have a self dot, I like to call it the dummy node, equals a self dot node. It has none as its data here, and it has no front, it has no back. And what we're going to do here is we're going to say self.dummy node dot next is the self.dummy node, and self.dummy node dot previous is the self.dummy node. Points to itself. So when we start off a brand new list here, scroll down here, we're going to have the dummy node here has none for data. That's how we know we got to the dummy node. We have nothing here. Its previous is itself, and its next is itself. Now what this is going to let us do is we will never have a none. Its next will always have a value. Its previous will always have a value. So the thing that comes first in my circular doubly linked list is always the dummy node's next. Whatever dummy node next is the current front node, even if we're empty. If we're empty, it's the dummy node. Whatever comes before it is always the last thing, even if it's itself. If it's itself, we're empty here. So we will always have a node to deal with here. So by using the dummy node, when I add to front, I don't need to do any of this nonsense here. I can just add in between the dummy node and the dummy node's next. Sorry, the other direction for you. Whether or not there's a value there. So we're going to make a new node. So the new node then is equal to self.node, given the item. Its next is going to be the dummy node's next, because it'll become the new front, right? So self.dummynodes.next, and its previous will be the self.dummy node. Always. So the thing that comes before the first thing is always the dummy node, right? The first thing is the thing that comes after the dummy node. So, and we never have nones, so this code just works, right? And really now we can just set that as self.dummynodes next, because this is never none here, will equal a new node, and now I have a new front, right? And we can say, hey, the next is this one here, and the previous is this one here. We can use our named parameters, make that hopefully a little cleaner here. So we're adding it between those two. I got a little long. Let me bump that down here. How's that? Right? So adding the back, same thing. We don't have to do any of this other stuff. I guess we should check. We don't even have to check if we're empty or not. We do the exact same thing here, except now it's our self.dummy nodes previous, right? Because the thing that comes before the dummy node is always the last thing, equals a self.node, given the item. The previous to the last thing should be the old last thing. The last thing should always be self-dummy nodes previous. So I'm sorry, the next thing then should be self.dummy node. Dummy node. So the last things next should be the dummy node, because we're making the whole circle here. And then the previous thing should be the self.dummy nodes previous. Right? The thing that comes before you is what used to come before the dummy node. Right? So now removing the front here, again, we should probably check if we're empty or not here. Now I don't need to do any of this other nonsense here. I can just grab the front item, and then I'm just going to jump over it here. So Now I'm going to do the exact same code more than once here, so I'm just going to call remove node given the self.dummy nodes next, right? The number of items go down by one, so then we'll say item equals this remove node, and I can return the item, and I can even move that into here. And we can even move the check is empty to remove node, right? So then our remove back here, then we can do the exact same thing. We can actually just return that, right? Just return. There we go. One-liners here. I love it. Where'd it go? Turn the remove node dummy. So to remove the back thing is the dummy node's previous, right? So now all we have to do is write our remove node. So define remove node, given a node, then first we're going to check if we're empty or not. So if self dot is, or we'll check is empty, I guess, self dot check empty, right? If we're empty, remove turn on value error, right? That didn't work very well here. Otherwise, we can remove the node. So the node I'm removing, all we need to do is jump it out. So I'm going to take the item is the nodes.item. I'm holding onto that. So to take an item out of a doubly linked list here, let's scroll up, we've got a doubly linked list here. Let's say the 7, right? So this one knows what comes before it and knows what comes after it. I'm going to grab that item here. Okay. Yep, so we're going to say, hey, thing that comes after me, if the thing that comes before you is now the thing that comes before me. Hey, thing after me, don't point to me anymore. Your previous is the thing that's my previous. Hey, thing that's before me, I don't come after you anymore. What comes after you is the thing that comes after me. We jump it out of the list. So we'll grab the item, and then we can say my node.next.previous is equal to the node.previous, right? Set the next thing's previous to my previous. Jump over me. And then node.previous.next, a thing that comes before me, I don't come after you anymore. My next comes after you. Return the self.number of items, -1, and return the item. Return the item, right? So no matter what node it is, I can, as long as it's not the dummy node, and we're going to check if we're empty or not. We're not going to ever remove the dummy node. We're only going to remove an actual first or an actual last. Otherwise, we're empty here, right? We can always jump it because I always have something there. There's never a none because you can't set a none's previous. You can't set a none's next. But because we always have something here, the code will always work for me, which is beautiful. So check is empty here. Where's our is empty here? So we can't say the front item here. This will be the dummy node's next item. And this will be the dummy node's previous item here. And then if my self.dummy node.next is self.dummy node, I guess we should just check our number of items. Return self.number of items equals 0. We're empty. That's probably easiest here, right? So all of our code here now is way simpler here. Adding to the back is just 2 lines. Adding to the front is just 2 lines, right? Removing is just, it's a couple lines here, but it's the exact same operation here. Just jump it out, get rid of it here. Removes it, it's gone. Yeah.
So when it gets removed, is that just automatically cleared back?
Eventually it'll get cleared out, yeah, because nothing references that one anymore, so the garbage collector can pick it up and say, oh, we don't need this anymore. Yep. Yeah, then at some point it'll get removed somewhere. Yep.
It's kind of just wasted space.
No. Yeah, so it'll get cleaned up eventually. Yep. So all these things become way simpler once we have that dummy node, right? Versus the other non-circular where I had to track a front, I had to have a back, and I had to know if they were nuns or not here. So the only reason to do this is because it's easier for our code, right? We don't really gain anything. It has the exact same functionality here, performs the exact same way. It's just easier to read and write. Okay. So we like these circular doubly linked lists with dummy nodes. Now, at this point, we're not completely a list yet because I can't get something by index or insert at a given index. Right? So let's add those operations here. And this is where linked lists are bad. Right? All these other operations, super fast here, right? But saying, hey, I wanted to get at a given index here. So let's add another function here. So define, just call it get maybe, or get index. Get index. I don't know. Is that fine? Get from index? Sure. Get from index. Front into from. Oh my goodness, from index. So first we should sanity check, is the index valid? Okay, so we're going to check first to see that it's greater than or equal to, or I don't know, as long as we're not empty, right? So we're going to check to see if we're empty. Maybe we'll write a helper function here. So we'll have a self dot validate index, given the index, validate index, given an index. So if self dot is empty, read the value error, empty or something, empty. And then if we're not empty, then we can check if my index is greater than or equal to the self dot number of items, then it's invalid. I don't have an index 7 when I have 7 items here. We'll raise an index error. I don't think I need a message. We'll just call it an index error here. Right? If it's not one of these, we're probably fine. Right? We didn't crash. We didn't throw an exception. Raise an exception. We should be good here. So to get something from an index, then I have to go find it. I have to walk all of those links here. Say, okay, let me go get to that value here. Okay, here's the 0, here's the 1, here's the 2, here's the 3. Because I can't just jump to it. I don't have that contiguous block of memory here. And this is where it's going to be really slow. So we'll say the current then is self dot dummy nodes next. Okay, so this is my current node here. We'll say current node. That's probably easier. Current node. Now, now we need a current index is 0. And while my current index is less than the index, I'm going to take current node equals the current node's next. Just go to the next chain. Go to the next chain. Go to the next one. Go to the next node. 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 We'll take current node plus 1. We're just counting here, right? We could do probably a for loop up to that value. That might be easier too. I don't know. I like the while. Is that silly? Should we do a for loop instead? This is okay. Right. Do you want to do the for loop as well so you can see it? All right. So you can say for index in range, oh, for node in range index here. We'll say current node equals current nodes next. Is that cleaner? I guess that's cleaner. We'll comment those ones out here, right? So if it's 0, I don't go anywhere. I'm still at the current node. If it's 1, I'm going to go 1 time. Right? If it's 10, I'm going to go 10 times, whatever it happens to be here. So I know it's a valid index. We'll get to the last one here, right? When we're done, we can return current node's item. Whatever's at that current node, whatever item it's storing here, here's the piece you wanted, right? Now, how fast is this here? Well, it is always O of n, because I have to walk n thing, or really, what is it, n minus k, or k minus n, whatever it happens to be here, still O of n essentially here. Now, if we wanted to be cute, we could make it sometimes faster to say, hey, if your index is closer to the end, let's count backwards. Sure, we've saved a little bit of time here. That might be nice here, but that's okay. So we'll leave it as a to do. To optimize eyes going backwards from end if index is greater than length divided by 2. Does that make sense? And we can just count backwards instead of counting forwards. That's all. Not very interesting here. Still going to be slow, even if it's halfway slow, right? Still going to be a slow operation, and that's not good, right? And then removing from a given index, like popping something off here. If we define a pop for an index, now if you don't tell me, we're going to give you the last one here. Otherwise, we'll get you a given index here. So if index is none, we can return self dot remove back, or remove back, right? If the index is none, that's fine. Otherwise, then we'll go count to that index, right? We have to get to that node here. So we'll go current node. We should validate it, right? Validate it, get to the node here. I guess we can return the item too. Oh goodness, what happened here? Didn't tab it in. So if the index is none, give you the back here. if we're already empty, it's going to fail anyway. That's okay. Otherwise, we'll validate the index, have the current node, go find the current node here. Again, we can optimize. That's fine here. We're not going to return the item just yet here. So we're going to have the item, right? Is the current node item, right? And now we need to remove that node. So to remove a node, right, we have code for that, right? We have a remove node. All we're doing is removing that node, right? It'll jump the things over it here and fix it for us here. Oh, yes, we can just actually return that. So you can return self.remove node given the current node. Okay, whatever node we walked to, go jump it out and give that item back. Right? So just go find it here. So again, this is still going to be slow though. It's not slow because things have to shift. It's slow because we have to get to that location. Right? So this was still slow with lists here because everything had to shift. This is slow with linked lists because we have to get to the nth node, the kth node, right? I'm slow to find the node to remove by index. So anything dealing with indexes is going to be slow because I have to walk all of those links here. All right. Excuse me. All right. So I think we're a list now. So right, we do all the things lists do. We can remove items by index. We can get items by index. Right. Oh, we didn't insert at a given index. So we'll add an insert here. That's the last one here. So we'll add a insert here that takes an index and an item. So first we should validate the index, right? Make sure let's do a quick little sanity check here. Um, I guess if we're empty, then we can just add it to the front. Or if index is 0, we can add to the front. I think we're probably okay. We'll just sanity check it. So self.validate index. We have the index here. Make sure it's a valid number. And then we have to go get to that node. So same idea here. We'll go find that node here. So current node, go get to the node. Now I have the same code a bunch of times. I should probably turn that into a function, right? Um, So we could even do that with the validate index. We could make validate index return that node here, right? That might be nice, or raise an exception. Let's go do that here. So we'll go to declaration. So it is empty. If it's not empty, then let's go return the node. So we'll say current node equals self.dummy node dot front or next here, and then for index or node in range index, current node equals the current node's next, and then we can return the current node. Okay, so now my validate index here, we can go find our usages here. Go to find usages. There we go, a couple places. Get from index. So now all of that then gets to be current node equals validate index, right? Cool. And where else do we use it here? Insert. Oh, okay, we were about to do that. So our current node equals the index there, and then our pop, where would we do that? Our validate node. Here's our current node will equal that one here. Cool. All right, I think we got them all here. All right. Where were we? Our insert. So once we have the current node here, this is, so if I wanted to insert an index 6, I now have index 6. So I need to go before that one, become the new index 6. So now my new node equals self.node. And then do I have an insert between? Did I add one of those add between? I didn't. Yeah, just a remove. Okay, that's fine. Oh, I didn't finish all this code here. My bad. We're not quite done yet. We had the same issue where we never fixed our links here when we added. So let's go add a helper function. We'll add a helper function. This will make life a lot easier for us here. So to do that then, let's call add between. So we'll have a self dot or add between that takes the previous and the next, or the, I don't know, the item previous and the next. We should go next and previous, I guess, right? I don't know if it matters. Next and previous, because the other order is next and previous. So to add in between then, I'm going to say a new node equals self.node. given the item, its next is the next, and its previous is the previous, right? Great. Now my new node's next previous needs to be me, and my new node's previous next needs to be me. So the opposite of when we removed it, we need to put ourselves in and make sure the thing that comes after me knows I come before it. The thing that comes before me knows I come after it, right? All right. So now we've got our add between. So now we can use the add between. So self dot add between. We're going to go in between. So we want my next to be the current node. So here's the item, and then my next should be the current node. What comes before me should be the current node's next. Oh, I'm sorry, previous. Right. So current node will come after me. Current node's previous will come before me, and I'm going to go in between those two. Right. So now I can fix up my helper functions up here. So dummy node. So we want to just add between. So we'll say self.add between. Here's the item, right? And we're going to go in between. So if we're adding to the back, the thing that comes next then will be the self.dummy node, right? And the thing that comes before me is the previous, is the self.dummy node's previous, right? It comes after me. Whatever came before it now comes before me because I'm the new back. And for the front here, same idea, self.add between. Here's the item. The thing that comes next now is the self.dummy node's next. The thing that comes before me is the self.dummy node, right? Because I'm the new front. We'll add in between those two, right? And again, hopefully that makes our code pretty clean here. No matter what add operation it's doing, insert in between, it just puts it in between, tells the thing that comes before and after it, I'm in the middle now. If we're removing, it says tells the things but before and after it, I'm no longer here, jump over me. So same idea with our double links here. And we should be able to add in between. So it adds in between, and then make sure we're increasing our count here then, right? So self.number of items plus equals 1 when we add in between. So now we don't need to add any items here, right? It's just even better, right? Just a one-liner, one little helper function. Like removing was removing a node, checking he's empty, removing from the back, getting the front, getting the back is empty. Cool. So I think we're in pretty good shape here. So um, inserting then is going to be slow, right? This will be an O of n operation or O of k and minus k. Again, the more n I have, the longer this is going to take because I have to go get to the node first. It's not inserting that's the slow part, it's getting to there that's the slow part. So we come back on Tuesday, we can take a look at, or no, sorry, Thursday's project day. We might have time to finish this out. We'll see how far we get. We got to talk about the project one. We'll talk about the new project we'll be working on. And then there's a way to make this even faster, which is cool, right? So that these inserts are not as slow. There's another trade-off we can do to make these faster, right? Which is pretty cool. So we can trade off a little bit more memory, a little bit more space complexity to make these a lot faster. And this is where linked lists will start to really shine because you can be really fast for your adds and removes if you know where you're adding and removing from. So we're gonna track that given location here. It'll be a lot of fun. So let me go commit this. Again, this is all new. Links are funky here, dealing with what's next and what's next and what's previous and what's previous and next and previous. And it's a little weird to jump through here. Again, I don't really like how the textbook does all of it. So my example looks a little different than his. They do the exact same thing. These are linked lists here. Let me push that one out. This one probably, we didn't test that one, but it probably works here. We should be good to, we can try a couple real quick, right? So for number in range, let's go 10. Let's go make a new um, list is a circular doubly linked list here. My list, sure. My list dot add to back the number, and then while not my list is empty, print my list dot remove from the back here. Let's do them in reverse here. And we didn't test all of them here, but we got 98765432210 back out. We can do more exhaustive testing would be good here. Writing some unit tests, those sorts of things would be good. But for now, we'll probably call it okay, and then we'll come back Thursday, do the projects, see if we can finish this out. If we don't have time, we can go to the next Tuesday and go from there. Okay, because we still should do a lab with linked lists. Uh, it'll be fun. We'll see. We'll see how it goes Thursday. Okay. All right. Anything else? Awesome. Thanks, folks.